In this video, we're going to be talking about binary to hexadecimal conversion. So as you probably know, binary is a base 2 system, okay? So every digit is represented by either 0 or a 1, whereas hexadecimal is much larger and allows for much more compact display of data, where it allows us to it's used in digital systems because it provides a compact way to represent binary numbers. Since one hexadecimal digit corresponds to exactly 4 binary bits, it's much easier for us humans to read and write large binary numbers by converting them into hexadecimal format, so it looks neater and is easier for us to look at and understand. And it also has many applications in computer systems and in networking as well, such as IP addresses and so on and so forth. But I digress. So back to what I was saying. So hexadecimal is a base 16 system. Okay, so it goes from 0, 1, 2, all the way up to 9. And then it starts with letters from A, B, C, up to F, where F holds a decimal value of 15, and this is 10, as well as 10, 11, 12, 13, 14, 15. Okay, and where every single hexadecimal digit can be broken down into 4 binary bits, as I mentioned. Okay, so let's say A can be broken down into, since it's 10 in decimal, we can break it down into 1010, where this is 8421. So 8 and 2 is equal to 10, correct? So that's what we have. So let's say we have a binary number that we want to convert into hexadecimal, since representing numbers in hexadecimal allow us to represent large binary numbers in a more compact way. So let's say we have the following number, and I'm going to write them down compactly first, actually, and then I'll write them down in a little bit of a neater manner. So let's say I'll start with a small number. Okay, let's say we have 110011. Okay, this is the binary number that we have, and we want to convert it to hex. How will we do that? Okay, first of all, we need to break it into chunks of 4 bits. So I'm going to start by taking these 4 bits from the rightmost side, starting from the least significant bit. So I'm going to take 1100, and then I'm going to leave a little bit of a gap, and I'm going to put 11, which is these two, right? Which is these two right here. And then they have 2 trailing zeros. So just since there's nothing on their left, you can think of them as trailing zeros. So these carry no weight and they don't add anything to the value of the number. Okay, and then we're going to take this and we're simply going to convert it from the binary value to the decimal value, and then from decimal value to the hexadecimal. So this corresponds to, I'm just going to write the weights of the numbers up here. And this is also 1, 2, 4, 8. This is an important point, right? Because these numbers it doesn't go 1, 2, 4, 8, and then 16, 32, 64. We start over again for the next 4 binary bits. Okay, so here we have 3, and here once again we have 3 because we only have, we have 2 and 1, 2 and 1, so we have 3, 3. And then just putting them together, you have 33. So this is our number in hexadecimal. This is simply how you represent it. This is our number in hexadecimal. So we went from 110011 to 33 in hexadecimal, where it's not actually 33. It's not 33 in the decimal sense, because if you actually break down the binary number, you will see that this isn't 33. This is larger than 33, because if we actually break it down, we have 1 plus 2, if we look 1, 2, 4, 8, 16, 32, you'll see that we have 1 plus 2 plus 16 plus 32, which gives us 32 plus 16 plus 2 plus 1 is equal to 51. Okay, and another way to check this as well is the weights of the hexadecimal number. So since it's a base 16 number, the weights are 16 to the 0 and 16 to the 1. So if we do 3 times 16 to the 1 plus 3 times 16 to the 0, you're going to get 3 times 16 to the 1 is 48. And then 3 times 16 to the 0 is just 3, since any number to the power of 0 is 1. So this is once again 51. And you can see that these two numbers match and that this is correct. Okay, so let's go ahead and do a few more examples. I'll pick a little bit of a larger number so we can see what is going on here. Let's try this one. So let's take the following binary number. Let's take 11110001. Okay. So once again, start by breaking it into chunks of 4, starting from the least significant bit. So this is our first chunk. And this is our second chunk. This is lucky. We have an 8-bit number, so it looks nice, and you don't have to add any trailing zeros on the left side to compensate for the missing values. I mean, that's just to make it seem clearer, and it's a 4-bit number, right? So this binary number, as we can see, if we take this one here, you have 0001, which corresponds to 1, 2, 4, 8. These are the weights that go with the number. So this in decimal is just 1, okay? Which in hexadecimal is also just 1, okay? And this gets converted to 1111. We have 1, 2, 4, 8. So if we add 8 plus 4 plus 2 plus 1, you get 15, okay? And 15, we know in hexadecimal, is equal to F, okay? So if we put this together, 11110001, binary to hexadecimal, we get F1, and that's that. And I'm going to go ahead and do one more example with a way larger number that you can start to see the reason why we choose to convert from binary to hexadecimal for a much more compact way of representing the number. So let's do the following number. I'm probably going to need a little bit of bigger space, so I'm just going to go ahead to the next page. So if we take 1000000, I want to make sure I have the right amount of zeros, 5 zeros, and then 111001. Okay, once again, start breaking it into 4-bit chunks, starting from there. 1, 2, 3, 4, 1, 2, 3, 4. Okay, so this is going to be at least 3 digits right here, 3 hexadecimal digits, right? So we're looking at a 3-letter word. You can think of it as a word, whatever you want to think about it. So let's start with this one, 1001. That is 8 plus 1, so it is 9 in decimal, which is also just 9 in hexadecimal. Okay, so remember that. We work with this one, 0011. That is simply, if we look at the weights, once again, I'm just putting these for clarity, you get 2 plus 1, which is equal to 3. Okay, and the reason, let me just actually cover this if this is unknown to some of you. The reason it's 3 and we're not considering 8 and 4 is because the digit in this spot is 0. So 8 times 0 plus 4 times 0. So as you can see, we're multiplying the digit by its weight, and adding all these together. So you get plus 2 times 1 plus 1 times 1. Okay, so this is what remains. This goes to 0 and this goes to 3. And then if we take this part, we know that this is simply just going to be 8 because it's 1000, and this is just 8. Okay, so now just bringing this all together. So we have an 8 and a 3 and a 9. Okay, this is going to be 839. Okay, sorry, let me just double check this. Yeah, so that's going to be 839 in hexadecimal. Okay, and if we go ahead and check this, you can convert this to decimal, where we simply do the following, where this is 16 to the 0, this is 16 to the 1, and this is 16 to the 2. And then if we add this up, where it's 8 times 16 to the 2 plus 3 times 16 to the 1 plus 9 times 16 to the 0, we get 8 times 16 to the 2 is 2048, plus 3 times 16, you're going to get 19, plus 9 times 16 to the 0, which is 9 times 1, is equal to 9. So you get 2048 plus 19 plus 9, which is 2076 in decimal. Okay, so as you can see, this is a pretty big number, and we compact it into the following hexadecimal number, so it looks much smaller, much smaller, and it is a much more compact way of storing our